our last section of material out of chapter 27. It's section 27-5, and it deals with torque on a current loop. It also deals with something called the magnetic dipole moment. So let's think about a current loop that's inside a magnetic field. I'll let my magnetic field be this direction. So I've used some blue arrows to indicate that I've got a magnetic field. It's a uniform magnetic field, and it points directly to the right. In this, I'm going to put a loop of wire, and to make it easier as far as the math, we're going to let that wire be a rectangular loop. So let's see. So I've got this rectangular loop. I'm going to let the current go in this way. Let's follow the currents going this way, this way, this way. And finally it's going to come out here. So there's my loop. I'm going to label these points, the corner A, B, C, D. And this loop, I'm not going to go over the mechanics of how it's assembled, but it's free to rotate about an axis that's going to run right like this. Okay. That would be our axis of rotation. We're going to let this side be the length of the loop, L, and we're going to let this side be the width, W. This also has a width of W. Okay. What we want to do is we want to actually find the torque on each one of these segments. Well, remember what torque is? Our torque, in this case, is going to be our force times our lever arm. So, first of all, we recognize that segments AB and CD are parallel to the magnetic field B. What's that mean? Well, it means that when we get the force for those two segments, that force is going to be ILB sine theta. But theta is going to be 0 degrees. Sine of 0 is 0. So the force will equal 0 on those two segments. So the torque is equal to 0 for segments A, B, and C, D. They don't have any inclination to rotate or to move or to do anything. So that's those two segments, okay? No force because the current this way, in this case for DC, it would actually be sine of 180 degrees, but that's also 0. If we look at segment AB, the current is actually in the exact same direction as the magnetic field B. The angle between those would be 0. Again, no force, there's no torque. So that's not the interesting segments. All right, so let's look at just segment BC. We know the torque is going to be the force times the length in this case. The force is ILB. In this case, if we do sine theta, the current is going straight up and it's perpendicular to B. So in this case, sine theta is going to be sine 90, which is going to turn out to be 1. And I guess I better be careful here. That is going to be, let's write it out with words, force times lever arm. Well, if this is the axis of rotation right here in the middle, then this lever arm actually has a length of W over 2. It's half of the width. Okay. That's going to be the torque on BC, or if we get rid of that sine theta, the torque on BC is ILB. How did I rearrange it? Do I want to leave it like that? I think I'll leave it like that. W over 2. If I do the segment DA, segments BC, let's do DA. DA also, it's this segment straight down here, it's perpendicular also to the magnetic field. So we're going to have the same situation. Oh, I tell you what, let's finish BC. I want to do one more thing before we go over there and talk about AD. I want to look at the direction of the force. If the current is up and B is to the right, I put my fingers up, B is to the right, and this side, this segment feels a force that's into the plane. It wants to go that direction. So I'm going to put into board. That torque has a direction. We can see the direction. It's going to be in the direction of this force. If the current is up, B is that way, there is a force into the board. The torque is going to want to rotate so that it moves into the board. All right, if we look at the other section, that's going to be section AD. Again, it's ILB. It also is at a 90-degree angle. It's pointing straight down. This is a 90-degree angle that it makes with the magnetic field. So sine of 90, W over 2. Let's see what its direction is. If the force, my fingers are down, and I have to curl them this way. Oh yeah, it's down. It's hard to hold my right hand, and then over. This side is going to feel a force out of the board. If it's free to rotate about this axis, this is going to want to go in, this is going to want to come out. It's going to want to actually take, or picture this piece of paper, the lip that's flat like this, and rotate it till it sticks out like that. This side wants to go in, this side wants to go out, it wants to rotate. That's actually going to be a really important idea when you're working on your electric motors, which is going to be your lab for the next couple of weeks. All right, so that one's into the board, that one's out of the board. If you were to look at it from above, if this is the axis from above, this one's causing a counterclockwise rotation. It wants to go that way. This one also causes a counterclockwise rotation if you look at it from above. So they're going to actually add together so that our total torque is, well, notice they're exactly alike except for this factor of 2 and this factor of 2. So it's like you have 1/2 ILBW, and this is 1/2 ILBW. So with a little rearranging, we get the total torque, the sum, is IL. I'm going to move this W inside for a minute. WB. Look at this. That's the area. What we find is our torque is IAB. That's the amount of torque on a single loop that lies in the plane with a uniform magnetic field in the way that we've drawn it, okay? Now we did that with a rectangular loop, but it turns out, and we're not going to do it with any more complicated math, that it does not depend on the shape of the loop. So most of the time those loops aren't going to be rectangles, so actually probably be circular loops. But what we're going to find is, for a single loop, that torque is equal to IAB. If we have lots of loops, we have N, that's the number of loops, then our torque is going to equal to NIAB. Okay, now we looked at a situation where our coil was not making an angle with the field. That's not necessarily always going to be true. We often have a situation that looks like this. If the coil makes an angle with the magnetic field, in this case I'm going to let the magnetic field point to the right again. Here's a loop of wire. Whether it's circular or rectangular really doesn't matter. We measure the angle that it makes from a normal or a perpendicular. So there's a normal segment to the loop. This is the direction that B is going. So that would be our angle theta. Notice B is our blue lines here. That's our little normal section, okay? In this case, the torque becomes NIAB sine theta, and theta is equal to the angle between that normal segment, that normal to the loop, and B. A lot of times if you want to think about a loop, like say this around the edge of this sheet of notebook paper is a loop, I think of the normal segment sticks right out of the middle of it, kind of like a handle. So here you can see, if I play this way, the marker points directly at me. If I point paper this way, that marker's, it's like a handle. Okay. So that's our formula that gives us the torque on a loop. Okay. You can see this as that torque rotates or moves around, that angle changes, the amount of torque is going to change. This part of the formula right here has a special name. It's called the magnetic dipole moment. The symbol for that magnetic dipole moment is a mu. That's a little unfortunate because we do use that for a lot of things already, but it's N-I-A. It is considered to be a vector that has the same direction as the area, which really is this direction of that normal. The normal to the area is what they're talking about when we treat area like a vector. In which case that changes this formula to torque equals mu b sine theta or, even better, torque is equal to the magnetic dipole moment cross B. Again, sometimes we have to do a cross product. Sometimes we can just look at it like this. Really, this formula is also perfectly good. Lots of information on that page, so take a few minutes. You may want to write that down. Make sure you've got a handle on it. I want to do one problem. Okay, this is also an example out of your textbook. It's example 27-11. In it, we have a circular coil with a diameter D equals 20.0 centimeters and 10 loops. That means N equals 10 when we're doing our formula. The current in that loop is 3 amps. It's placed in a magnetic field with a magnetic field strength of 2.00 Tesla. And they asked me to do two things. Find the maximum and the minimum torque. Well, if I go back to my formula, the torque is equal to NIAB sine theta. The number of loops isn't going to change. The amount of current doesn't change. The area, which is just the area of our circular coil, doesn't change. B doesn't change. The only thing that changes is sine theta. Okay? The minimum torque is going to be when sine theta equals 0, which is going to happen at 0 degrees or 180 degrees, right? Our maximum is going to happen when sine theta equals 1. Sine theta is going to equal 1 at 90 degrees. The magnitude of torque will also be the same at 270 degrees. It'll just be a directional difference. So let's go with the maximum torque when sine theta equals 1 is NIAB. That's 10 loops. That's 3 amps. That's an area that is pi r squared. So pi, and then r is 0.10 meters squared. There's our pi r squared times our magnetic field, which is 2. And that gives me a maximum torque. That comes out to be 1.88 Newton meters. Of course, we already mentioned that our minimum torque is 0. And of course, here, like I say, we're talking about magnitudes, not necessarily directions. Okay? That's the end of section 27.5. That's all the lecture notes over chapter 27. I do think I will look for an example of performing a cross product. I think there's a cross product on your homework, and I want to make sure you remember how to do a vector cross product. So look for that other video.